this chapter, we will be using calculus as a tool in curve sketching. In this lesson, we will be applying the curve sketching procedure to various functions.
All right, everybody. So we're going to take a look at some curve sketching today, and what we're going to do is really just that. We're just going to sketch a bunch of curves. Okay. Now, to start off with, just to review the procedure that we're going to follow here, the very first thing that we're going to do is we're going to look for the domain of every function. Okay. After that, we're going to take a look at the intercepts. Okay, the x and the y intercepts. The third thing that we're going to look for here is we're going to take a quick look at symmetry. Now, that may or may not be a significant thing in a graph, but we're going to look for it anyway. The fourth thing we're going to look for here is we're going to look for asymptotes. Then we're going to move on and we're going to take the derivative. We're going to look for intervals of increase and decrease. With that, we are going to look for maxima and minima, right? Points that are maximum points and minimum points. 7, we're going to look for intervals of concavity. And then finally, we're going to look for points of inflection or cusps. Okay, one of those two there. After that, with all that information, we're going to put that all together and draw a quick sketch of the graph. But again, the best way to kind of see this happen or to understand how this happens is actually to see it happen. So I'm going to go through and do a handful of examples. We're going to break this into 2 videos. So I'm going to do a few in this one, and then I'll do a few more in another video. All right, now the first function here that we're going to graph is 8x over x plus 1 squared. Okay, so number one, we're going to take a look at the domain, and actually because it's a rational here, you can tell pretty quickly where the issue is going to be with the domain here. I cannot allow x to be equal to -1. Okay, because if I do, then the function becomes undefined. So that's it. That's the gap in our domain. So it's pretty straightforward. 2, the intercepts. Okay, well the first thing that I'm going to do here is I'm going to look for the y-intercept, basically because I'm lazy and I'm going to grab the low-hanging fruit first. Y-intercept is so easy to find. All I really have to do is evaluate the function at 0. Right? We just let x go to 0 because whenever x is equal to 0, that's going to be a point on the y-axis. And when you do that, you can see right away because of that numerator, you're going to get 0 up there, but the denominator won't go to 0. The denominator is going to go to 1. 0 plus 1 is 1, squared is 1. So I'm going to get 0 here. Now, that's a pretty good indication that this graph is going to go through the origin, because when x is equal to 0, y is equal to 0. I'm still going to look for my x-intercepts here, because I could have more than just that one x-intercept, although I know already that there's going to be one. So in this case, you let the y-coordinate go to 0, and that's going to be 8 multiplied by x over x plus 1 squared. Now notice that I've got my fraction here equivalent to 0, but bear in mind that that won't happen when the denominator goes to 0. In fact, there is no value that I can plug into the denominator that'll make this thing equal to 0. So really, it's just about the numerator going to 0, and that's only going to happen when x is equal to 0. So really, the only point here that's significant in this discussion here is the origin. Okay, that's going to be both the only y-intercept and the only x-intercept. Okay, 3, let's take a quick look at symmetry. And to investigate the symmetry, basically what we do is we plug in -x and see what happens here. So if I plug in -x into the numerator and -x into the denominator, okay, well, a little something funky happens here in the denominator. When I multiply the numerators together, I'm going to get -8x, and that's totally okay. But down in the denominator, I run into a little bit of a weird situation here. I've got a -x plus 1. So what I'm going to do is I'm going to factor the negative out of this binomial. Okay, but I'm not going to factor it out of the square quite yet. I'm going to do this in steps. I'm going to factor it out of what's inside the brackets. Okay, I've still got the brackets where everything underneath there is being squared, and now I'm going to distribute the square to both the -1 and the x minus 1. But when I do that to the negative 1, that's a coefficient, negative 1 squared is simply going to become positive 1, and so it disappears. And so I'm left with, when I plug in a negative in here, negative 8x over x minus 1 squared, which isn't the negative of the original function. It's also not exactly equal to the original function. So what this means is this is neither odd nor even. So it doesn't have either one of those types of symmetry that we associate with either odd or even functions. So it's not symmetrical in any significant way that I would graph, or I could make use of while I was graphing here. Okay, let's take a quick look at the asymptotes. Okay, now I already know that this has got an essential discontinuity at x is equal to negative 1. So I'm suspecting there's a vertical asymptote at x equals negative 1. Now, what I should probably do is just investigate the behavior of the graph in and around negative 1 here. So I will take the limit as x approaches negative 1, let's say from the left. And I'm just going to go back up to my original function here. Let's take a quick look. If I let x approach negative 1 from the left, well, okay, the numerator really doesn't have any problems with that. If I just take a number really, really close to negative 1, but to the left of it, so like negative 1.1, negative 1.01, whatever, the numerator is going to become negative. When I do that to my denominator, a number that's slightly less than negative 1 plus 1 is going to be a number that's slightly less than 0. Just think about your number line there. Okay, here's 0, here's negative 1. If I take a number just slightly to the left of negative 1 and add 1 to it, I'm going to get a number that's still slightly negative. But when you square it, it becomes positive. So the numerator is negative, the denominator will become positive, which means this is going to go to negative infinity. In fact, anytime that I'm investigating the behavior around an asymptote, it's either going to go to positive or negative infinity. I know that. I should say a vertical asymptote. If I now take the limit as x approaches negative 1 from the right of f of x, basically the exact same argument can be made here. The numerator is still going to be negative, and because of that square, that denominator is still going to be positive, so I'm still going to get negative infinity. So as we get closer and closer to negative 1, the graph is dropping down. Okay, it's dropping straight down. Now, does this graph have a horizontal asymptote? Well, we can figure that out just by comparing the degrees of the numerator and denominator. The numerator is linear, the denominator is quadratic. Yeah, it will. This is going to have a horizontal asymptote at y is equal to 0. That's what happens when the denominator's got a larger degree than the numerator. The denominator will grow faster than the numerator, causing the whole thing to collapse to 0. Good. Okay, now we're at the point where we can turn over to calculus and investigate what's going on here by using some of the calculus we know. So we're going to take the first derivative. Okay, so y primed is going to equal, now I'm going to use the quotient rule on this one. So the derivative of the numerator will be 8, and then the denominator was x plus 1 squared, minus the numerator multiplied by the derivative of the denominator, which will be 2 times x plus 1 to the 1, multiplied by 1, because the derivative of x plus 1, all over x plus 1 squared. Okay, well that's kind of busy. So what I'm going to do is I'm going to factor some stuff out here. I can take out an 8 out of the numerator. I can also take out an x plus 1. That is going to leave me with x plus 1 from this first term, minus, I took out the 8, I took out the x plus 1, so I'm left with a 2x there. X plus 1 to the 4th. We still see that? There we go. Move that up a little bit. Okay, now I can cancel out one of the x plus 1s there. Now that's so long as x doesn't equal negative 1, but I've already established that that's not true. So I can actually cancel that, and I'm okay. I've already covered my butt there. This is going to leave me with x plus 1 cubed down in the denominator. And up here I'm going to get, what is that? That's going to be negative x plus 1. And I'm probably going to factor the negative out of that and just make that negative 8 x minus 1 all over x plus 1 cubed. Okay, now I am curious as to the intervals of increasing and decreasing for this particular function right here. So what I'm going to do, and this is a tool that I've used way back when we first started exploring calculus here. I'm going to take a quick look at how this function behaves by splitting it into its individual functions. So I'm going to take a look at the number line here. Notice that this function here goes to 0. This x minus 1 is going to go to 0 at 1. So I'm going to put a 1 in there. And the denominator goes to 0 at negative 1. So in the numerator, I've got this negative 8. And as a function here, negative 8 is just going to be negative everywhere. It's going to take on negative values here, negative here, negative here, negative here, negative here, because it's always negative 8. There's no variable there to cause it to change values. It's always negative 8. No matter where you are on the number line, that function is always negative 8, so it's always negative. X minus 1, on the other hand, if you look at how it behaves all by itself, and by the way, that's what I'm doing. To figure out how the behavior of the whole function works along the number line, I'm going to break it into its individual pieces and look how each piece behaves. So x minus 1 takes on a value of 0 at positive 1. And then if we take in values to the right of positive 1, it's going to be positive. And if you plug in values less than 1 into here, it's going to be, it's going to be negative. It's going to be negative if you plug negative 1 into that. Negative 1 minus 1 is negative 2, and then negative for anything less than that. If you plug x plus 1 into this, and we will include the fact that it's cubed, x plus 1 is going to go to 0 at negative 1. Anything to the right of that, any value of x to the right of negative 1 will cause x plus 1 cubed to be positive. Anything to the left will cause it to be negative. Now, I have taken the individual pieces, okay, of this function and looked at how they behaved. So now I'm going to put it all together to create that function. Notice that these first two terms are in the numerator, so it's going to be a negative times a negative divided by a negative will be negative. So the whole function will take on a negative value if x is less than negative 1. At negative 1, it's going to be undefined because that 0 is in the denominator. Between those two values, between negative 1 and 1, I'm going to have a negative times a negative divided by a positive. That'll be a positive. Here, at negative 1, it'll be a negative times 0 divided by a positive. That's just going to be 0. And then for all values of x greater than 1, I'm going to have a negative divided by a positive times a positive. Well, that's just going to be a negative. So what I see here is that f of the derivative, no, sorry, I should have put f prime of x there because I am looking at the derivative. The derivative is less than 0 on negative infinity up to negative 1, and then from 0 out, sorry, not 0. Sorry, my mistake. It's 1. It's the interval from 1 out to infinity, which means that the function is decreasing on the interval negative infinity to negative 1 union positive 1 out to infinity, but we include the positive 1, okay, because we include the endpoints where they exist. Now in this case we didn't include the negative 1 because the negative 1 didn't exist. It was undefined there. My derivative, however, is positive on the interval negative 1 to 1, and then we include the 1, and that was it. So the function is actually only going to be increasing on that interval from negative 1 to 1. And I shouldn't have, I should not have included the 1 here because the 1 is making the function equal to 0, which means it's not, wow, totally forgot to put the 0 there. Okay, so anyway, so there you go. So now we've determined where the function is increasing and where it's decreasing. Now, really quickly, we can slide in here just before I get to the end of the page. I'm going to have to flip over in a second here. But we can do number 6 here real quick. We're looking for maximum, minimum points. Well, the only point that even looks like it qualifies as a possible maximum or minimum is when x is equal to 1. Okay? And when x is equal to 1, I can tell right now because it is the end point of an increasing sequence and the beginning point of a decreasing sequence here, or interval. I know that this is going to be a local max. Now, it's also the only max here. It could be an absolute max. I'm going to have to take a quick look at the way that what else is happening on this graph, but that could be an absolute. Now, I do want to figure out what the y-coordinate is, so I'm going to go right back to the original function. If I let x go to 1 here, the numerator becomes 8. The denominator becomes 2 squared, or 4. So this is just going to be the point 1 comma 2. And that's where we're, whoops, sorry, can't see that. That's where we're going to get our local max. Fabulous. Okay, now, that was 6. Now we got a couple more things to do here. We got to take a look at concavity. So I'm just going to take a quick look here. My derivative was negative x minus 8, sorry, x minus 1. Negative 8 times x minus 1 over x plus 3 cubed. So let's take a look at, whoops, get this all together. Step 7. My first derivative was negative 8 multiplied by x minus 1 over x plus 1 cubed. And just because I don't trust my memory, I'm just going to double check that. Yep. So now, in order to investigate intervals of a concavity, I'm going to take the second derivative of that. And just like before, I'm going to use the quotient rule. So, the derivative of the numerator here will be simply negative 8 multiplied by x plus 1 cubed minus the numerator, negative 8 x minus 1, multiplied by the derivative of the denominator, which will be 3 x plus 1 squared, all over x plus 1 cubed squared, or x plus 1 to the 6th. Okay, now I will take out whatever's common here. And what I see is common here is a negative 8 and an x plus 1 squared. Okay, and when I do that, I am left with, out of my first term here, x plus 1 minus, now bear in mind that I've got the minus the negative, but I took out the negative 8, so that negative stays behind here. I took out an x minus 1 square, I took out an x plus 1 squared, so that one's gone. And so I'm left with 3 multiplied by x minus 1, all over x plus 1 to the 6th. Okay. We can cancel out a couple of those x plus 1s there, so this is going to be negative 8. This will be x plus 1 to the 4th in the denominator. And then in the numerator, what do we got here? Well, we're going to have an x and a negative 3x, so it's going to be negative 2x, a 1 plus a 3, so plus 4. Looks like, I'm just going to double check that, looks right. Up here, I am going to take out the negative 2. When I take that out, that'll be positive 16, x plus 2 over x plus 1 to the 4th. Now, once again, I'm going to take a quick look at the behavior of this function to see where it's positive or negative. So, again, I'm going to draw myself my little number line here because I'm going to take this thing apart and look at its pieces. The denominator goes to 0 at negative 1, and the numerator goes to 0 at, oh, sorry, I put that in the wrong spot. It's going to be negative 2 for the numerator, negative 1 for the denominator. Okay. Oh, shoot. No, I was anticipating, I'm sorry, that little pause there was because I know what this is supposed to look like, and I can almost hear people saying, wait a minute, you screwed that up. And yeah, I did. When I factored out that negative, that should have become a positive. Sorry, I knew that that negative 1 was supposed to be the one on the farther right there, so it should have been negative 1 and positive 2. Those are those two spots that I need to consider for the way this function behaves here. So I've got this 16 here, this function 16, and it is positive everywhere because it's just the number 16. X minus 2 is going to be 0 at 2, positive to the right, and negative for every value, every interval to the left. X plus 1 to the 4 is going to be 0 at negative 1, and then because of the 4th power there, it'll be positive everywhere else. And so now when we put that second derivative together, in this interval over here to the left of negative 1, I'm going to have a positive times a negative divided by a positive, that'll be negative. Positive at -1, it's a positive times a negative divided by 0, that's undefined. Here it's a positive times a negative divided by positive, that's going to be negative. Here, that 0 is in the numerator, so it's going to be 0, and then it's positive over here. So what I'm seeing here is that my second derivative is positive, okay, on the interval from 2 out to infinity, which means the graph here is going to be concave up on the interval from 2 out to infinity, including the 2. Okay, so the second derivative is positive on the open interval, it's concave up on the closed interval. The second derivative is negative, okay, on the interval from negative infinity to -1, okay, not including the 1 because that's where it's undefined, union, and then it's going to be -1 out to 2, which means this is going to be concave down on the interval negative infinity to -1, again, not including the -1 because that's an asymptote, union the interval from -1 to 2, and including 2. So right away, once we take a look at this, we can actually go to step 8 and we can identify our points of inflection. And in fact, I've really only got one candidate for this because I've only got one point here where the graph here the function here, the second derivative goes to 0. The only other place that might have been a concern is where it was undefined, but we know right from the beginning that was an asymptote here. So the only number here that could be an issue here is going to be where x is equal to 2. And actually that does qualify as a point of inflection here because it changes from concave down to concave up. So good, point of inflection. All I'm missing now is the y coordinate. So let's go back to our original function. If you plug 2 into your original, 8 times 2 is 16. 2 plus 1 is 3, squared is 9, so it's going to be 16 over 9. 16 over 9, so a little under 2. Okay, so those are our 8 pieces. Now, let's put this all together. Okay, so here's my graph. I know that I've got an x-intercept right there. In fact, my x and my y-intercept are right there. I know that this graph had a vertical asymptote at -1. I know that it has horizontal asymptote at y is equal to 0. I knew that it wasn't symmetric here. Now, in terms of the first derivative, and I got to go just take a quick look back here. The first derivative, what did it do here? It was negative until -1, then it became positive, 0, 1, negative. So when I take a look at my graph here, here's my -1, here's my 1. I'm going to just take a quick look. I'm going to draw a line up here to identify what's going on with my first derivative. There's a break here and a break here. It was negative, positive, and negative. Did I say that right? Yeah, negative, positive, negative. Good. Down here, I'm going to identify the interval where my concavity changed. And my concavity changed at -1, which I totally expected because that was my asymptote. And then it was out here at 2. Okay? And it was, what did I say here? It was concave down here, concave down here, and then concave up here. And that actually leads us to our other points that were significant. We had a maximum point at 1, 2. Okay, so if we put that right there, there's 1, 2 is going to be right there. And I've got a point of inflection at 2, 16 over 9, which is going to be a little bit less than 2. Okay, so what does this now look like? All the pieces are there, we just got to put it together. Well, in this section right here, I've got an asymptote here, vertical asymptote, horizontal asymptote here. The graph is decreasing and concave down. So decreasing and concave down. It does not cross the x-axis, and we know when we took the limit that it goes down to infinity. So the function's gotta look something like that. Okay, it's gotta look something like that. Now, on the right-hand side, it's increasing and concave down, and we know that it approached the vertical asymptote going down, so this has got to be coming up like this. It's got to go through our x-intercept right there. It comes up, it hits a maximum, okay? So the tangent goes horizontal right there, hits a maximum. At 1, it starts to go down, starts to decrease. It's still concave up though, still concave up until it gets to this point. It continues to decrease after that, changes to concave up, and approaches the horizontal asymptote. And so there it is. That's roughly what our graph should look like. Okay, let's take a look at another one. F of x is equal to x plus 2 to the 1/5 plus 4. All right, let's dive right in. The domain. Well, the only part of this that looks like there might be an issue here at all is this to the 1/5 here. But remember, taking the fifth root, you can take the fifth root of anything, whether it's positive or negative, 0, regardless. And so it doesn't really look like this is causing me much of a problem. So I'm assuming here that the domain is element of the reals. Okay, intercepts. Let's do the y-intercept first. Again, I like doing this one first because all I got to do is plug in a 0 and evaluate. And so when I do that, I get 0 plus 2 to the 1/5 plus 4. Okay. And so that is going to be the fifth root of 2 plus 4, whatever that turns out to be there. And I do believe this is going to be some number that's a little bit larger. Okay. Slightly larger than, I'm guessing 5. So slightly larger than 5. I can go to my calculator and figure that out if I need to. But anyway, there we go. So we got to get a decimal number in there. Let's look for the x-intercept now. I am going to make the y-coordinate equal to 0. So that's going to be x plus 2 to the 1/5 plus 4. All right. So basically, when you're looking for the x-intercept, you are solving an equation. So we're going to bring the 4 over. Negative 4 is going to equal x plus 2 to the 1/5. Now, to get rid of the 1/5 here, I'm going to take both sides of this, I should say, to the power of 5. So it's going to be negative 4 to the power of 5 is going to equal x plus 2. Well, negative 4 to the 5th, 4 is 2 to the 2, so this is going to be like 2 to the 10. So that's going to be negative 1,024. And then subtract the 2, negative 1,026. Ooh, that happens quite a ways to the left of the origin. Okay, but good to know. So those are my two values there. Let's take a look at what's next. Let's take a look at symmetry. I am going to plug in a negative into that, so I'm going to plug in a negative in for x. Okay, now in order to see what's going on here, I'm going to have to factor the negative out of that negative x plus 2. And that's going to leave me with negative x minus 2 all to the 1/5, because I do this in steps. Okay, I don't try to do this too fast. I do this in steps. First, I'm going to take it out of the binomial. So I'm still focused on what's inside the parentheses there. Now I've got a negative 1 times x minus 2 to the 1/5. I've got two factors there. So the 1/5 will distribute to both. But the fifth root of negative 1 is just going to be negative. So this is negative x minus 2 to the 1/5 plus 4. Now notice that this isn't the negative of the whole function. This is also not a situation where the negative disappears. So this is neither even nor odd. Okay, so there's no nice symmetry the way I would like to see it. So be it. No big deal. Okay, now asymptotes. Asymptotes. This is not irrational. There are no asymptotes. So that was easy. Kind of like it when that happens. Now, Before I move on to the next step here, I want to go back here just for a moment and point my finger right here. Notice that the domain is all reals. It's really important that you catch that the domain is all reals, okay? Because now I'm going to look at intervals of increasing and decreasing. So the first thing I'm going to do here is I'm going to take the derivative. And that's going to be 1/5 x plus 2 to the negative 4/5. And then the derivative of the 4 is going to go to 0. So that's not going to be an issue here. Okay, so I'm getting 1/5 x plus 2 to the negative 4/5. I am interested in where, and actually I might write it like this even. Okay, this is going to be the 5th root of x plus 2 to the 4th. Okay, now, couple of things here. Notice that this is undefined at x equals negative 2. As soon as you let x equal negative 2 here, this is undefined. But no matter what other value you plug into this, no matter what number you plug into this, other than negative 2, you're going to take it to the 4th power, which will make it positive. 5th root of a positive is positive times 5 is a positive 1 over. So essentially what's going on here is, if I look at my number line here, at negative 2, the derivative is undefined. But to the left, it's positive. To the right, it's positive. Meaning that this graph is increasing, okay, I tried to make a point a few seconds ago, so I've already started to set this up here, so hold on a second. So the derivative is positive on the interval negative infinity to negative 2, union negative 2 out to infinity. Okay? Now, this means that the function is increasing. Now, we got to be careful here. Bear in mind that although the derivative is undefined there, okay, although the derivative is undefined at negative 2, the original function isn't. The original function was okay with negative 2. If you plug negative 2 into this, you get the 5th root of 0, which is 0, plus 4 is just 4. So our graph has no problems with it. So what that means is this function is actually increasing on the interval from negative infinity up to negative 2 and including and continuing through out to infinity. It's always increasing. Okay? This is in fact, I would argue this is more than just monotonically increasing. This is strictly increasing. Because the derivative actually never has an opportunity to go to 0. Okay, well that's interesting here. What that means is for our step 6, for our max and min, there's no point here where the derivative goes to a maximum or a minimum. There is a spot here, okay, where the derivative is undefined. So we might think about that as being a critical number. Okay, the critical number of the function here, where x is equal to negative 2, but it's increasing and then increasing afterwards, so it can't possibly be a max or a min. So basically our conclusion is there's no maxima or minima. Okay, let's take a look at concavity. So now my second derivative, nice to have the first derivative just sitting right there. If I multiply by negative 4/5, it's going to be negative 4 25ths x plus 2. And if we subtract 1 from that, what are we going to get there? That's going to be negative 9/5. Right, okay, so that's negative 4 over 25, the 5th root of x plus 2 to the 9. Okay, well, let's take a look at our number line here. Once again, this is going to be undefined at negative 2. The original function is defined there, but the second derivative is undefined at negative 2. Now, if you choose a number for x that's less than negative 2, you're going to get a negative value to the 9, which will be negative. The 5th root of a negative will be negative. Multiplied by positive 25 will still get you a negative. But negative 4 divided by that, that's actually going to be positive. So it's going to be positive in this interval to the left of negative 2. To the right of negative 2, this will be positive. To the ninth, we'll create a positive. The fifth root of a positive is positive. Multiplied by positive 25 is positive. But when I take negative 4 and divide it by that, I'm going to get a negative. So my second derivative is positive on the interval negative infinity out to negative 2, which means the graph is going to be concave up on the interval negative infinity up to negative 2 and including. Again, remember it's defined there. The second derivative is going to be less than 0, okay, from negative 2 out to positive infinity, which means it's going to be concave down from, from negative 2 out to infinity, and including negative 2. And this takes us right to number 8 here, the possible points of inflection or cusps. This negative 2 here, in this particular case here, this does count as a critical number of the first derivative, okay, because it's where the second derivative is either undefined or 0, but at the same time, we've got the changing concavity, so we definitely have a point of inflection, okay? We definitely have a point of inflection there at the point negative 2, comma 4. And actually, based on how complicated this graph, I don't have much paper left, but I actually think I can just squish the sketch in here. Okay, and actually maybe what I'll do is I'll zoom in a little bit. I'll put the sketch in here. So I know that I'm going to have that point of inflection, and that's really the point that has jumped out at me a couple of times here, at the point negative 2, 4. I also knew that I had a y-intercept here at a point just slightly above 5. So there's my y-intercept. My x-intercept is way, way over there. No biggie. My first derivative, okay, there was an issue at negative 2, but it was increasing here and increasing here. My second derivative was concave up here, concave down here. Okay, now let's put this together. So in an interval where I'm increasing and concave up, it's swooping up like this. Now my x-intercept is way, way over here. So it's basically coming up like this, and it's curving up. Now here's what's interesting about this point right here. This is a point where the first derivative was undefined. Now think about that. The first derivative is the slope of the tangent, and it's undefined, meaning that this thing goes vertical. And that's what makes this particular question interesting. It's got a vertical tangent line right there. Okay, that's why the first derivative is undefined there. But it's defined at the function, where x is negative 2 is still defined in the function. I still got a point there, negative 2, comma 4. Then I'm still increasing, but concave down. So it's going to go like this through the y-intercept, and then it's going to continue to increase, but it's going to be concave down. So it's this special little graph right here, and that doesn't quite look the way I want it to. That's got a vertical tangent. So the graph goes vertical right at that point right there. Anyway, interesting graph. Okay, next we're going to take a look at the function f of x is equal to x over the square root of x squared plus 2. This has also got a kind of an interesting little feature to it that's worth spending some time looking at. First of all, let's take a look at the domain. Now when I see a radical there, and a denominator there for that matter, I'm concerned. But when I take a look at this here, first of all, when I consider the denominator, is there anywhere where this thing could go to 0? And the answer is no. Anytime I take a number and square it, whether it's positive or negative, I'm going to get a positive result. And when I add 2 to that, that's always going to be positive. So there's no way that this is going to become 0 here. And that's actually good news, because when I take the square root, what I'm trying to look for here when I'm looking for the domain is I'm looking for any time or any points along the x-axis where that creates the radical or the root of a negative. And I just said these are always positive, so that never happens. So actually my domain here is going to be x is an element of the reals. Beautiful. 2. Let's take a look at the intercepts. And again, I'm going to grab the y-intercept first. F at 0 is going to be 0 over the square root of 0 squared plus 2. And this is going to go to 0 as long as the denominator doesn't go to 0, and it doesn't. Because 0 squared is 0 plus 2 is 2, and then the square root of 2 here. So that's just going to be 0, which is good. The x-intercept, I am looking at, I am looking at where f of x equals 0, and that's going to be x over the square root of x squared plus 2. And remember, and I'd said this before, if I've got this rational expression here equal to 0, it's not the denominator doing that. Okay, the denominator can't create a 0 here, so it's got to be the numerator going to 0. So it's got to be where x is equal to 0. So notice in both cases here, my x and y-intercept both suggest that the origin is an issue. Okay, the origin is where this thing is crossing the axes. Good. 3, symmetry. Okay, so if I take a negative and plug it in, I am going to get negative x in the numerator, and then I'm going to get negative x squared plus 2. Now, bear in mind how that looks down here. I'm replacing the x with a negative x. Now, because in the original function x was being squared, when I replace it with negative x, it's negative x being squared. And that's actually just going to become a positive. So look what happens here. The negative basically disappears. This is essentially exactly the same as the negative of the original function, which makes this thing odd. Okay, so it's got, therefore it's got rotation symmetry about the origin. Whoops. Sorry, I wanted to say rotation symmetry. Good. Good. So actually, I can kind of guess at this without too much work. I can kind of do half of the work here, if you will, and still get the graph here. But that's okay. I'm going to go through and do the whole thing anyway. But that's just going to, basically, when I'm done here, if I look at my graph and notice that it's got rotation symmetry on the origin, I know that everything's nicely consistent here. 4, asymptotes. This is a rational, so I am going to be expecting an asymptote here. Now, it's going to have no vertical asymptotes, because the denominator doesn't go to 0 here. But have a quick look at this. Notice that the degree, and actually I'll write the function out again here. Notice that the degree of the numerator and the denominator really are the same. Okay, it's a linear in the numerator, it's a linear in the denominator because it's the square root of an x squared. Now, I'm going to take the limit then as x goes to infinity of x over the square root of x squared plus 2. I want to see how this thing behaves as I go really, really far to the right. Now, when I do that, when I get really, really big values of x, when you square a billion, adding 2 really doesn't change the value significantly. So when I get really, really big values of x, this plus 2 is essentially irrelevant. And so then I've got the square root of x squared, which, when you think about it, everybody, is kind of like the absolute value of x. Now, when I go to positive infinity, it doesn't really matter because I'm going to get positive numbers squared, which is a big positive number. The square root will be a positive number, and then it's basically x in the numerator. So this is going to simplify down to x over x, or just 1. Which is kind of neat. But the behavior is a little, whoops, sorry. Dang it. I'm anticipating the answer. When I go to negative infinity, something a little different happens here. When you go to negative infinity, bear in mind, just look at the denominator here. When you get really, really big negative numbers here, like negative a billion squared, again, adding the 2 does nothing to it. So I'm really just looking at this. When you take a negative number, a really big one, and square it, you get a positive. The square root of a positive number is a positive number. But bear in mind, I'm taking the limit as x goes to infinity, negative infinity. So the numerator is going to be negative. The denominator will be positive. but they're going to be the same value? Because really what this is like taking the limit as x goes to negative infinity of x over the absolute value of x. So even though they got the same number, the numerator is going to be negative, the denominator is going to be positive. This is basically going to be -1. This is what makes this graph unique, is I've got two horizontal asymptotes. I've got a horizontal asymptote at y is equal to 1 and y equals -1, depending on which direction you're going. That's why this was an interesting question to look at. Now let's take a look at intervals of increasing and decreasing. Now at this point here, actually, to be honest with you, we could probably draw a half decent sketch even right now without having to go through the rest of this. But it is what it is, so let's go through, let's do the calculus here. So f primed of x, let's figure what that is. So again, I'm going to use the quotient rule. So the derivative of the numerator is 1, and then multiplied by the denominator, x squared plus 2 to the half, minus the numerator multiplied by the derivative of the denominator to the -1/2 multiplied by 2x all over the denominator squared. Okay, well, I got a bunch going on here. Now, first of all, notice the 1/2 and the 2 are going to cancel. The smallest exponent on the x squared plus 2 is actually -1/2, so I'm going to take that out. -1/2. That is going to leave me with 1 minus, and notice I've got two x's there, so 1 minus x squared all over x squared plus 2. That's going to drop down to the denominator, so I'm going to get 1 minus x squared all over x squared plus 2 to the 3/2 when I bring that down, because this is all to the 1, and I'm just going to add that 1/2 down there. So I want to double check that I did that right there. Oh, shoot. No, I didn't. No, I did not. Okay. I'm sorry. I didn't take out... I got to go back up a step here. I did not take out x squared plus 2 to the 1/2. I took x squared plus 2 to the -1/2. So when I factor that out of x squared plus 2 to the 1/2, I got to divide those powers, which means subtracting exponents. When 1/2 minus -1/2 is 1. That actually is going to leave me with an x squared plus 2 there to the 1 minus x squared. Oh, this is a lot nicer than I was about to make it. Whoa, wow, I'm glad I caught that. Now, again, for those that aren't seeing how that works here, it might be more obvious if you just multiply this through. If you just multiply this back through, you'll see x squared plus 2 to the -1/2. If you multiply that by x squared plus 2, it'll get you x squared plus 2 to the +1/2. So anyway, right now that factor up front there is going to move down. The x squared is going to cancel. I'm going to be left with a 2 here. That's beautiful. Absolutely beautiful. Now, where is this function go to 0? It doesn't. Okay, because the numerator is just a constant and it's 2, and so there's nothing here that's going to cause it to go to 0. Where is it undefined? It's not. So whatever value this is taking on, it's always going, and I mean value, I mean sign, whether it's positive or negative, it's always going to be either positive or negative here. And it turns out this thing is always positive. Okay, so we know that f primed of x is greater than 0 on the interval here where x is an element of the reals. That means this thing is positive or increasing on the interval -infinity to infinity. In fact, it's strictly increasing. It is always increasing. That was wonderful. And so as a result, I can also jump to point 6 here and say there's no max or min here. Okay? There's no point that even suggests a maximum or a minimum. And I really like that first derivative here. Now, let's go through and let's investigate the second derivative. Let's take a look at concavity here. So let's just remember that function, 2 over x squared plus 2 to the 3/2. Okay, so this is 7 now. my first derivative was 2 over x squared plus 2 to the 3 halves. And actually, I might write this as 2 multiplied by x squared plus 2 to the negative 3 halves, just because this is going to make the derivative a little easier. My second derivative will now be multiply through, that's going to be negative 3 x squared plus 2, what is that, to the negative 5 halves, multiplied by 2x. All right, so what does that look like? Negative 6x over x squared plus 2 to the 5, whoops, that's not 100% clear, but to the 5 halves. Okay, now what does this tell us? Well, I'm interested once again in where the second derivative is positive or negative, is positive or negative for concave up and down, but I'm interested to find that where it goes to 0, or it's undefined. But just like the first derivative, look at that, that's not going to become undefined anywhere, so it's really just where it goes to 0, and it's going to go to 0 at 0. So this actually makes things a little bit easier. So if I plug in a negative value squared, just look at the denominator, negative value squared plus 2, 5 halves, the denominator will always be positive no matter what I plug in. So it's really just the numerator that's the issue, and if you plug a negative into that, the numerator becomes positive. If you plug a positive into the whole thing, the numerator becomes negative. So this tells me the second derivative is positive on the interval negative infinity up to 0, which means this thing is going to be concave up from negative infinity up to 0 and inclusive. The second derivative is going to be less than 0 on the interval 0 out to infinity, which means it's going to be concave down on the interval from 0 to infinity, including the 0. And so clearly, number 8, if I'm looking for a point of inflection or a cusp, and in this case it's definitely going to be a point of inflection, it's that origin again, 0, where x is equal to 0. Okay? And I can see that because the concavity is changing at 0. Okay, got everything we need. Let's graph this thing. Whoops. So I knew that my origin was the intercept, the x and the y intercept here. I also know it's my point of inflection. Okay, I have got an asymptote here at 1 and an asymptote at negative 1. I know, however, that it's going to be approaching the positive one only as you go to the right and approaching the negative one as I go to the left. If I think about my intervals of increasing and decreasing, it's always increasing. And then if I think about my intervals of concavity, it's going to be concave up here. See, happy face. Concave down here. All right. So now let's just take a quick look at this. So in this interval here, to the left, it's increasing, concave up, and it approaches this asymptote as I go to the left. Well, it's got to look something like that. Then it becomes concave down, still increasing, and it approaches this asymptote. So it's got to look something like this. Now, notice it doesn't go vertical here because the first derivative wasn't undefined there. So it just kind of levels out. Well, it doesn't level out flat, but it's just got a reasonable slope to it, and away we go. That's what that looks like. Interesting graph because of the two horizontal asymptotes. All right, everybody, one more graph for this video here. So x squared minus 2x plus 4 over x minus 2, actually just a nice rational expression here. It does have kind of an interesting little feature to it, but there's really nothing too terribly extraordinary about this. First of all, number one, let's take a look at the domain. And I think that's pretty clear. X cannot equal 2. Now, normally I would take a look at my numerator and see if I could factor that down and cancel that out, but actually the numerator won't factor in a way that allows me to cancel. Like, I might look at this and think, well, is that a removable discontinuity or an essential one? But let's just take a quick look at the discriminant of the numerator. That's going to be negative 2 squared minus 4 times a times c. So that's going to be 4 minus 16. Notice that that's going to be less than 0. The whole point being, if the discriminant of a quadratic is a perfect square, then you should have been able to factor it. You should have been able to see something in there that could have simplified it. That's not going to factor nicely at all. In fact, it won't factor without complex numbers there. So that's good. That's good. 2, intercepts. Okay, well, first of all, let's take a look at the y-intercept here. So f at 0 will be 0 squared minus 2 times 0 plus 4 over 0 minus 2. And it doesn't take much to figure out that that's going to be negative 2. So our y-intercept there is going to be negative 2. The x-intercept will be where f of x is equal to 0. And that will be x squared minus 2x plus 4 over x minus 2. The denominator is not going to be responsible for that, so I could multiply through by the denominator. That's going to be irrelevant. X squared minus 2x plus 4. And actually, ironically enough, I just did the work on this. Notice that the discriminant, and I did that work up here to see if I could factor it, the discriminant was equal to negative 12, which means no solution. So there's no x-intercept. The y-intercept is negative 2, and there is no x-intercept. Okay, whoops. I don't know if you just saw that, but the lead of my pencil just went flying. Okay. 3. We're going to look at symmetry. Okay. Now I have a suspicion, I have a suspicion about this immediately, just because of the combination of odd and even terms here. So if I plug in negative x squared minus 2 times negative x plus 4, whoops, I don't know why I did that, all over negative x minus 2. Oh, sorry, you didn't see that. The negative here disappears because of the square. This becomes positive 2x. 4 doesn't change, and then I can factor a negative out of the denominator. So that the whole thing, I can take that negative out there, out of the whole thing, and make that x squared plus 2x plus 4 over x plus 2. But that's not the original. So it's not odd. And the negative didn't disappear, so it's not even. So this is neither odd nor even. Okay. Let's take a look at asymptotes. Well, I know that it's got a vertical asymptote. I know that it has an essential discontinuity that x is equal to 2. So the trick is just to figure out what's going on there. So if we take the limit as x approaches 2 from the left of our function, let's just go up here. If I approach 2 from the left, just think about my number line. So here's 0, here's 2. If I approach 2 from the left here, I'm going to get a number that's close to 2 squared. It's going to be close to 4. This is going to be a number that's basically close to 2. So negative 2 times that's going to be close to 4. So these are going to kind of cancel. I'm left with a positive. And if I take a number that's close to 2 but from the left and subtract 2, this is going to be negative. So positive over a negative, this whole thing down here, this is actually going to go to negative infinity. If you take the limit as x approaches 2 from the right, and okay, listen, I know what I'm doing is a little quick and confusing. If you watch it kind of again, hopefully you'll see what I'm doing here. I'm now going to let x approach 2 from the positive side. So I'm looking at what each piece here does. If I approach 2 from the positive side, x squared is going to get closer and closer to 4. Negative 2x is going to get closer and closer to 4, and again, those will basically cancel, and I'm going to be left with a positive 4 there in the numerator. This x is approaching 2 from the positive sign, which means it's slightly bigger than 2. When you subtract 2 from that, you're going to get a number that's slightly bigger than 0, so it's going to be positive, but it's really close to 0. Positive divided by a positive, it's going to get you a positive. So it's going to go up to positive infinity. So basically, if here's 2, it's going to go down on this side, up on that side. Awesome. Now, because the degree of the numerator is greater than the degree of the denominator, it doesn't have a horizontal asymptote, but it might have an oblique one. So we got to check into that. So what I'm going to do here is I'm going to do the division. X minus 2 divided by x squared minus 2x plus 4. Okay, well I can get rid of the leading term there by multiplying my divisor by x. So x squared minus 2x. Well, that's beautiful. And when you subtract that, it all goes to, basically, what if I subtract down here, I'm just going to get a 4 there. Which means the degree of my remainder is less than the degree of my divisor, so I'm done. So essentially, x squared minus 2x plus 4, okay, divided by x minus 2 is going to be the same as just x plus 4 over x minus 2. Essentially what we're saying with that remainder is there's this little piece left over that still needs to get divided by x minus 2. I'm just not sure what to do with that. Now, as I let x go off to infinity, positive or negative infinity, notice that this piece right here, because the x is in the denominator, this piece is going to go to 0. So I'm just going to be left with x. And so there's my horizontal asymptote, or sorry, my oblique asymptote. Y equals x. Now, I can do one other little thing about this, okay? Just when I take a quick look at this. If I want to know how this thing is going to behave, when I take the limit as x goes off to infinity of this thing right here, it's going to equal the line y equals x plus, if I go to positive infinity, I'm going to get a positive number divided by, now bear in mind, I'm going to infinity, so this is going to be a positive number. So this is going to be just slightly larger than x. So here's my line, y equals x. As I go this way, it's going to be equal to x, the line, plus a little bit. If I go this way, it's going to be equal to the line, but now this will be a positive number divided by a negative number, because remember, if I go to the left, I'm letting x go to negative infinity. This denominator will be negative, so it's going to be the line plus a small negative number, so it's going to be here. So essentially the graph is going to come below the line to the left and above the line to the right. Just because of this piece right here either being positive or negative when I let x get really, really big in either direction. So I have a little bit more of an idea of how this is behaving just by looking at that right there. And like in a previous question here, that's actually enough for me to have a pretty good idea what this graph looks like. I could probably draw it from at this point right now. But let's take a look at the derivative. So 5. So when I take the derivative, and I'm going to take the derivative using again, the quotient rule here, that's going to be the derivative of the numerator multiplied by the denominator minus the numerator multiplied by the derivative of the denominator, which in this case is just going to be 1, all over the denominator squared. Now, in this case right here, there's really nothing that I can factor out. The best that I can really hope to accomplish here is just to simplify the numerator a little bit. So I'm going to multiply this out here. That'll be 2x squared. What do I get here? Minus 4x minus 2, so minus 6x plus 4. Minus x squared plus 2x minus 4. So that is going to get me x squared, what do I got here? Minus 4x, and that's it, over x minus 2 squared. Okay. And actually I can factor that numerator, make that x times x minus 4 over, x minus 2 squared. Okay, so now I got my pieces here. I'm going to use my little chart over here to investigate how this is behaving. I know there's going to be an issue at 0, 2, and 4. 0, 2, and 4. Okay, those are all of the pieces where my pieces here have issues here. So let's start with x. And again, all I'm interested in is signs. So it's going to be 0 here, positive, 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 and negative there. X minus 4 is going to be 0 here, positive here, negative, 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 negative in the intervals and at those numbers. X minus 2 squared is going to go to 0 at 2, but because of the square, it's going to be positive everywhere else. So now I can put this all together to get my function, which will be a negative times a negative divided by a positive, positive. A 0 times a negative divided by a positive is going to be 0. Positive times a negative divided by a positive will be negative. Here I'm dividing by 0, so undefined. This is going to be negative again, 0, and positive. So my function, and now I'm running out of room here, so I'm going to have to kind of speed this up here. My function is positive on this interval and this interval, okay? So that means my function is increasing on the interval from negative infinity to 0, and then including the 0, union, and what's that going to be? 4 out to infinity. This thing is decreasing on the interval 0 to 2, but not including the 2, because the 2 is going to be the vertical asymptote. Union, then it's going to be from, oh, it looks like 2 again, out to 4. Okay. Okay. And actually, because of this right here, we can put this together. I'm going to just slip 6 into here, the last little bit here, because take a look at this. What I've got here, I've got an increasing sequence ending at, increasing interval ending at 0, and a decreasing interval starting at 0. Increasing, decreasing. Well, that means 0 is my max. And we already saw that that's going to give, that is my y-intercept at -2. So I'm going to have a max at 0, -2. I have also got an increasing sequence interval. I keep saying sequence, that's not what I mean. An increasing interval that starts at 4 and a decreasing one that ends at 4. So decreasing to 4, starting at 4, which means I'm going to have a minimum at 4, comma. Okay, now I got to do a little bit of work here because I got to figure this out here. That's going to be 4 squared will be, I'll just do it over here, 16 minus 8 plus 4 over 2. So looks like, what is that, 6? 16 minus 8 is 8, plus 4 is 12, divided by 2 is 6, yeah. So way down here, we're going to have this minimum at 4, 6. Whew, good. Almost there. Now we got to take a look at concavity. Okay, let's remember our function here. Let's take the derivative of this one right here. X squared minus 4x over x minus 2 squared. So the derivative was x squared minus 4x over x minus 2 squared. Is that right? Whoops. Is that right? X squared minus 4x over x minus 2 squared? Yeah. Okay, good. Now let's take the second derivative so we can investigate concavity. Almost done here. Almost done. That is going to be 2x minus 4. That's the derivative of the numerator, multiplied by x minus 2 squared, minus the numerator, multiplied by the derivative of the denominator, that's kind of big and bulky, over x minus 2 squared squared to the fourth. All right, what can we take out here? Well, oh, actually, you know what? I'm going to factor just a little bit more here, just so that we see everything. So I have got a 2, x minus 2, x minus 2 squared, minus x minus 4, to x minus 2 over x minus 2 to the fourth. I just wanted to make sure that everything was factored, so when I pull stuff out, it's clear what I'm doing. Okay, I've got an x minus 2 here, an x minus 2 here, and 2 factors of 2. So that's what we're going to take out. 2 x minus 2. That is going to leave me with x minus 2 squared minus x minus 4. Okay, well that wasn't... Sorry about that. That wasn't quite as useful as I was expecting it to sort of be there. Okay, well one of the x minus 2 terms factors cancels, so this will be 2 multiplied by, this will be x minus 2 in the denominator cubed. This will be x squared minus 4x plus 4 when I expand that x minus 2 squared, minus x squared plus 4x. Oh, I like what I just saw there. This is looking good because that will cancel with that. That will cancel with that. I'm left with just 4 times 2. That is beautiful. That just became 8 over x minus 2 cubed. Well, that was outstanding. So, my second derivative here, okay, doesn't ever go to 0, but it is undefined at 2. If you pick any value of x less than 2, that binomial becomes negative, and the cube is going to keep it negative. So it's going to be negative here, and then on the other side it'll be simply positive. So my second derivative is less than 0 on the interval negative infinity to 2, which means this thing is concave down from negative infinity to 2. Second derivative is going to be positive on the interval 2 to positive infinity, which means it's concave up from 2 to infinity. And this, and I'll plug in point 8 here, this should clearly illustrate that we've got a point of inflection here. Concavity is changing at the point 2, comma, yeah, I don't know what it is. Oh, I'm sorry. I'm sorry. Oh my gosh. Yeah, okay, this is lack of caffeine talking. Okay, I'm going to just come back up here and I'm just going to delete all of that. Yeah, clearly I need to have a little bit more caffeine today. Keep awake here. Hoy. Everybody, I do know that it's undefined at 2. I do know that the function's undefined at 2. So there is no point of inflection. What that was that's an asymptote. And that's why the behavior is changing on either side there. I'm so sorry about that. This has been a long one. Let's just jump right to the sketch here now. Okay. I know that this thing had a y-intercept here at like -2. I know that it had an asymptote here at +2. In fact, that was the issue. I should have known that to begin with. I know that it had a maximum value here. And I know that it had a minimum, and I think it was at 4,6. So it had a minimum right there. Now, it's interesting that the maximum is less than the minimum. But that's because this thing, whoops, sorry, my graph isn't going to do me justice here. But I also had this horizontal asymptote here, y is equal to x. I know that it approached 2 this way, and the x is equal to 2 this way and this way. And so I can also look at my derivatives, and my second derivative here. I know that it was increasing here. It was increasing here, decreasing here, and then it was decreasing and increasing. I know that it was concave down, and the only change in concavity was at 2, so it's concave down here, concave up here. So here's what's going on. It was increasing concave down up to the y-axis, and it was approaching this asymptote, so it was doing something like this. Then it's decreasing concave down and approaching the asymptote here. It was decreasing concave up, coming away from the asymptote, approaching our minimum, and then it's increasing concave up and approaching the asymptote there. And so that is roughly what this graph is going to look like.